Okay, so we're going to solve this problem. We have refrigerant 134a. It's a working fluid in a vapor compression refrigeration cycle. The evaporator pressure is 1.8 bar and superheated vapor exits the evaporator at -10 degrees C. And the compressor isentropic efficiency is 88%. The condenser pressure is 8.6 bar and subcooled liquid exits at 30 degrees C. So the mass flow rate of the refrigerant is 6 kilograms per minute, which turns out to be 0.1 kilogram per second. And you're asked to determine the rate of heat transfer to the refrigerant passing through the evaporator, the net power input into the cycle, and the coefficient of performance. Well, we generate a quick system, so we have all of our devices and states labeled. And let's do it this way. So what do we have? We have a compressor, followed by a condenser, followed by an expansion valve, followed by an evaporator. Our traditional numbering of states is 1, followed by 2, followed by 3, followed by 4. And often the assumption that coming out of the evaporator is saturated vapor, but for this problem superheated vapor exits the evaporator, so it's superheated vapor at the -10 degrees C. So I'm just going to make it clear, like, no, that's not the case anymore. They've modified it. And likewise, we come over to state 3, and often we have saturated liquid coming out of the condenser at that saturation temperature of the condenser. But here, it's going to come out subcooled liquid at 30 degrees C. So I'm going to put just SL at 30 degrees C, and then take this off, that it's not saturated liquid coming out of the condenser. All right, the condenser pressure is given. It's the 8.6 bar, and the evaporator pressure is given 1.8 bar. So 1.8 right here, 8.6 right there. Okay. So there's quite a bit of information given. The mass flow rate, let me just write it like this. The mass flow rate is 6 kilograms per minute, which is 0.1 kilogram per second. All right. Then the next thing we want to do is put a sketch. We can put a number of diagrams, but let's go ahead and put the temperature entropy diagram, put the dome, and then we'll have a line of low pressure, and that low pressure is the 1.8 bar evaporator pressure. And then we'll have another line of higher pressure coming across, and that line is like 8.6 bar. If you wanted to, you could go and look for the saturation temperatures for both of those, which we can find later. But what we want to do, well, let's do it right now. 1.8 bar. If we come over here, the 1.8 bar is around a -12 degrees C. So if you wanted to, you could put in here, this is like -12. I know it's not precisely -12. I think it's a -12.7 something, but it's close to that, -12. All right. And then for the 8.6 bar, let me see if I have that one. No, not there. Come across. Actually, here it is, -12.73 for the 1.8 bar. That's a saturation temperature out of the superheated table for refrigerant 134a. Okay. And then if we go to our 8.6 bar, it'll be in between the 8 and the 9 bar So it'll be in between 31 and 35, and it's around what, 30 something. So it's not precise that we need to know that, but let's go and let me see if there's a better way of doing that. Let me see if there's another table I can look at. Maybe table A11 as a function of pressure. Let me see. I don't have that. Let me go get it. So if we go to the table A11, it doesn't have a line of 8.6 bar. It's in between, so you can tell that the saturation temperature is somewhere, you know, what is that? 60% of the way from 31 to 35. Let's say it's around 34. So if you wanted to, we could put in here that's like 34. Okay. Okay, let's continue on. Let's put into our diagram where our state 1 is. It's coming out slightly superheated, so it'll be right around there, meaning the temperature is -10, 2 degrees higher. And so that's where state 1 is. We're going to undergo an isentropic compression, then adjust with the isentropic efficiency of 88% to come out with state 2 actual, being up here on the 8.6 bar line at some elevated temperature. And then we're going to condense. Normally we would stop the condensation at saturated liquid, but it comes out slightly subcooled. And so 3 is off into subcooled liquid, and it was subcooled down to 30. So there you go, that's state 3. Then you put it through the expansion valve, and it goes out to state 4. So that's our loop. Let me kind of clean this up a little bit. We're going to come across and up a little to state 1. Then from state 1, not straight up, but a little to the right on a TS diagram to state 2. Then we'll condense, cool it first, desuperheat it, then condense it, then subcool it down to state 3 in the subcooled liquid region, put it through the expansion valve, and there's at state 4. Well, to help us, we make a table to collect all of our properties. So here's our state, and we're going to have state 1, and we're going to do this isentropic compression, then adjust it for the actual compression. So I'm going to put 2s and then 2 actual for state 2, and then state 3, and then state 4. And we're interested in the properties of pressure. We could put it in bar, put it in kilopascal, doesn't matter. Just have to, if we're going to use software to evaluate our properties, have to have the right pressure units. And then temperature in degrees C. We could be interested in the quality, and primarily the enthalpy in kilojoules per kilogram, and the entropy in kilojoules per kilogram Kelvin. Okay, so some of the information's given to us. Let's go ahead and put that information in first. The pressures. Pressure at 1, well, that's our 1.8. And then it jumps up to 8.6, 8.6, 8.6, and then back down to 1.8. So we have all of our pressures. The temperature, well, at state 1, it was coming out slightly superheated at -10, and we don't know what happens after that. I mean, if you wanted to, you could make a little note. I like to do that. Put a note out here, and then say, okay, this is slightly superheated. And we know our tables to help us evaluate properties. So for refrigerant 134a in our textbook they're using, we have table A10, A11, and A12. So if it's two-phase liquid vapor and you know the temperature is the primary input, use A10. Or two-phase liquid vapor pressure table, that's a primary input, use A11. And then if it's superheated, use table A12. So I would say, okay, we're going to probably find properties out of table A12. It's superheated. Okay. And when we look at it, at state 2s and 2 actual, they're both superheated and superheated. Okay. And then state 3, so we're just going to be in table A12 for a little while. And then for state 3, your subcooled liquid. Now we're going to use an approximation where it's a subcooled liquid, and we'll probably use table A10. And then for state 4, you're in a two-phase region, two-phase liquid vapor mixture, and we know the condenser, evaporator pressure, and so it'd be like table A11. All right. Okay, so for the enthalpy, you have to be able to look up at 1.8 bar negative 10 degrees C. Well, this is slightly superheated. Let's see what I have for this one. That's A11. Here's table A12. It's in the superheated refrigerant R134a. We're at the low pressure of 1.8 bar. And we already talked that the temperature, the saturation temperature is -12, but we're coming out at -10 degrees C. So along this line is all -10 degrees C. And we pick up that enthalpy to be H at 1 is here, as well as S, the entropy at state 1. So those are the two values, 242.06 and 0.9363. So let's go back to our table. So we have 242.06 and 0.9362. All right. Well, the assumption, we do it in 2 steps, so we just bring this down for state 2s, 0.9362. And now the question is knowing this pressure and entropy, can I get the enthalpy, H? Well, it's a little bit of work. We have to do some interpolation. And I don't know if I have that interpolation. Here it is. So we're going still in the table A12. We're not on a line of constant pressure, so we're going to have to go in between. Our pressure was at 8.6 bar, and our entropy was 0.9362, S 0.9362. So you look down in here and you say, well, that's in between the 40 and the 50 in this pressure block. And it's also between the 40 degrees C and 50 degrees C line in this pressure block for the entropy. Maybe I just put that 0.9362 falls in between, 0.9362 falls in between. So we can set up a interpolation using those values. You basically find that this is a fraction of the way is 60% with respect to pressure. And so what we can do is set up a mini pressure block of 8.6, and we'll set it up at a temperature of 40 and a temperature of 50. And you take this value of S and this value of S and you combine them. So it's 0.9374 plus 60% of the difference between 0.9217 and 0.9374. So the S value comes in, I'm going to look at my notes here, at 0.92798 at 40 degrees. You do the same thing for these two values, and you find that it comes in at 0.9624. Okay, and then you do the same thing for the enthalpies. You're taking this value and this value, you're going 60% of the way from here to there, and you find that that enthalpy comes in at 272.214, and then likewise at the 50 degrees C, 283.16. All right, now I'm going to change color because what we are really coming in is 0.9362. We look, is it in between? Yes, it is. What's that fraction of the way in between? That fraction looks like it's 0.238815, so about 24% of the way, 1/4 of the way. From the lower value to the upper value, we find our value of interest, use that fraction to get our enthalpy, and that enthalpy comes in at 274.83. That's a lot of work. But that's what you need to do if you're doing it by hand. If you have software, it's a lot faster. So we find that after a lot of work, we get this value right here, 274.83. Well, now we can find what is the work for the compressor if it was isentropic. Well, it's the difference between these two H's, and that minimum work, or the isentropic work, would be 32.77 kilojoules per kilogram. We have the isentropic efficiency of 88%, so the actual work of the compressor is not less than that, it's more. You divide by 0.88 and you find that it's 37.24 kilojoules per kilogram. So we use that to calculate our actual enthalpy. So H2 actual is H1 plus 37.24, and that comes in at 279.30. Okay, so a little bit of work there analyzing the compressor, but we got our enthalpy at 2 actual. Now we get our enthalpy at 3. Well, it's subcooled liquid. We're going to use table A10, and it's coming out at that temperature of -30. I'm sorry, not -30, 30 degrees. And so we use table A10. At 30 degrees, our enthalpy is H of F at 30. And so we bring over here, and it's 91.49. 91.49 kilojoules per kilogram. All right, how about going through that expansion valve? Well, we've done that a number of times. You do a control volume around it, steady state, no heat, no work, no change kinetic, no change of potential energy. It's isenthalpic. It's 91.49 kilojoules per kilogram. Okay, now that we have all of those, we're ready to answer some additional questions. If you like, I like to make another table to organize everything, and it's a table basically of the energy balances for each of the control volumes for the component, like the compressor, condenser, expansion valve, evaporator. And you don't have to do it, but you just say, what is my component or device? Let me put device. And we have a compressor, then we have a condenser, then the expansion valve is trivial, and then the evaporator. Okay, and then we're interested in what is our Q and our W, both in kilojoules per kilogram and kilojoules per kilogram. And because we want to sum this column, I'd like to stay with the traditional sign convention. So around this compressor, it's adiabatic, so the compressor is 0 heat transfer per unit mass going through it. But then the work is going to be negative because it's actually work in, not out. And we find that it's enthalpy 1 minus the enthalpy 2. So enthalpy 1 minus enthalpy 2, and it comes in at negative 37.24. Okay, the condenser. Well, it's no work in or out, and it's all heat transfer. And the control volume around the condenser, it's not into the condenser, it's actually out of the condenser. So it's going to be a negative, and we just know it's going to be negative, but it's going to be the difference in the enthalpy. So it's the enthalpy at 3 minus the enthalpy at 2 actual, and then that comes in at negative 187.8. Put another 1 there if you like. Now the expansion valve is a little trivial. I could have left it off, but there's no heat, no work. But there it is, the expansion valve. And then the evaporator is the heat added. And so you're picking up heat. You're going from state 4 to state 1. So it's H1 minus H4. You pick up 150.57. You do a sum of the Q's to get the Q net for that device or that cycle, and it comes in at negative 37.24. You do a sum of the works. There's only one work. It's negative 37.24. They are consistent, and so that's great. They're both equal. Okay. Now the next thing what we need to do is just answer our questions for part A. What is that rate of heat transfer passing through the evaporator in kilowatts? Well, this is Q dot in the evaporator will be the mass flow rate times lowercase q in the evaporator. All right, we found 0.1 kilograms per second. And then in the evaporator, 150.57 kilojoules per kilogram. And then Q dot in the evaporator comes in at the 15.0 whatever, 15.0 whatever. I just put 15.1, 15.06. Okay, fine. Kilowatts. Answer for part A. For part B, what's the net power input? Well, they want to get rid of the negative sign, so we'll just do the m dot times the negative of the work of the compressor. So 0.1, and you find it's equal to 3.72 kilowatts. That's W dot into the compressor. Answer for part B. And then the coefficient of performance, COP, is the ratio of what you desire. We desire a lot of heat removal. What's our heat removal? It's our 150.57 per energy input, 37.24 work input. So our coefficient of performance for this refrigeration comes in at 4.04. And that's answer to C. Well, I hope that was helpful.